All right, ready? Any questions, Bethany? Okay. We continue on where we left off last time. So what this is the basis of all, scientific research is what we're talking about today. So we're going to talk about the process by which, what's called the hypothetico-deductive method, but which is basically the way that everyone does science, here in UC Merced and every other campus. So the basic idea, if you wanted, if you're interested in some type of doing science, doing research, is that you start with some type of idea of what you want to do. And then what you do is you kind of read about it. So you go and you look at the literature and see what previous studies have done. And then you also, you tend to have a theory too. So the theory that you have kind of depends upon what your major is. So like how many here are psychology majors? No, all public health? So what's the major theory that we use to explain things in public health? Well, in epidemiology, you don't, right? Epidemiology is a descriptive type of thing. So, of field. So really epidemiology is just about describing. Epidemiology doesn't really tend to have theory. Epidemiology about maybe 20 years ago is that they started to go into what's called social epidemiology. And so, the way that epidemiology used to work is that it would be mostly board doctors and board nurses who would then go back and get an MPH. And so they would learn or get a PhD and they'd learn epidemiology. And epidemiology is just, statistics really. And so when they would go through and look at things, they would look at things like how, they would do some type of, it was mostly medical research. And so they were drawing upon their medical knowledge to come up with their ideas about how the body worked or whatever it's going to be. And what happened about 20 years ago is that they started to notice is that, in all of their kind of models about predicting behavior, the thing that always would come out is socioeconomic status. So like if they just threw socioeconomic status into any of their equations to predict, does red wine lead to better health or worse health? And so if you do that and you come up with all your theory about why red wine might be good for you or red wine might not be good for you, they found if you threw socioeconomic status in, is that socioeconomic status predicted? And so it kind of became the norm of epidemiology to throw socioeconomic status in there and treat socioeconomic status as if it was something that was kind of, like some type of internal thing that occurred to you that made your outcomes differ based upon your socioeconomic status. And so, but that was not very satisfying. And so they started to get into coming up with reasons for, why it is that socioeconomic status might be kind of important. And so it led to this whole era of what was really just bad epidemiology, because they didn't really have good theories. So what happened in public health after that is that really it's the growth of all the different areas of public health. So like, I'm trained as an economist. And so for me, when I look at problems, I look at them as an economist. That's the theory I draw upon. Other people, like especially in health behavior, health promotion, they tend to have psychology backgrounds. And so it means that when they do health behavior, they're looking at theories of behavior change from psychology, usually. So if you take health behavior or health promotion, is that they're probably going to teach you about behavior change theories. Environmental health, if you look like Ricardo Cisneros or Asa Bradman, who do environmental health, they were really trained as natural scientists, right? And so they come in and they do public health, but they're bringing their kind of discipline of natural science into it. And so public health tends to be a little bit different than other areas in that there's not like a single type of theory that we have. But having said that, you probably do get taught things like the ecological model, right? And probably in Public Health 01, they probably talked about the ecological model of health. So there are theories out there that public health uses. So it means that whenever you go through and that you're going to look at some type of issue, the first thing you do is you try and kind of figure out, well, what's your, what bent do you want to take up on it? And then what you do is that you go through and that you start to read basically the literature within that area first to see how they approach it. And then you might widen out and sort of read other areas as well. But what you're looking for is you're looking for what your what the underpinnings for how you're going to go through and approach the problem. It's the first thing. So then you go through a process, and we'll talk about the process of how you go from I have an interest to I have a research idea, because we sort of treat it as like this, like this magical process where you go and read a bunch of stuff, and then suddenly out pops some type of research question, and it's it's more involved than that. But let's just say that you do that and you get a research question. Then what you do is you propose it as a research question, and then you state it as a null hypothesis. And then you go out there and you make observations, so you gather data, and then you see, is my data consistent with my null hypothesis that and so do I support my research question or not? That's the basic idea behind it. The key thing in here is what's called operationalize, and we'll use this word a lot. Like, how do you operationalize something? Because what operationalize means, that's like, how do you go from some type of vague type of concept into exactly what it is you're going to do? So when I talk about like reading the methods section in a lot of detail, the methods section, the reason you read it is because that's where they operationalize. That's where they go from like saying, well, I'm interested in children's views on violent television, to what do we mean by children? What do we mean by violent views? How are we going to go through and measure it? That's what we mean by operationalize, how they actually do things. So that's operationalize. Then is you have to operationalize what your design is, so how you're actually going to go through and do things. Then you have to operationalize how you're going to measure it. Then you have to figure out how exactly you're going to collect the data, how exactly you're going to analyze it, and then how you're going to interpret it once you get the data, the results in. Okay, so let's take an example. Let's say that my question is it better to treat infections with Manuka honey or antiseptic? Manuka honey is a real thing, comes from a Manuka tree, and that it's little jar of it sells for about $30 a bottle. And the reason is because it's sort of known to have antiseptic properties. And so the question is it true? Does Manuka honey, lead to better wound, better healing than standard care? So let's say that's my question. I go out there and I read about it, and I decide that this is a good thing to test. And so I'm going to state it as my research question then is, Manuka honey is better at treating wounds than standard care. Then what I do is I state it as a null hypothesis, where I say, okay, the null hypothesis is that there's no difference between Manuka honey and standard care. And then what I'm going to do is get data to see whether or not I can reject my null hypothesis and conclude that no, Manuka honey is better than standard care, or whether the data supports my null hypothesis that there's no difference between Manuka honey and standard care. Okay, so I want you to pair up into groups of 2 or 3 and come up with this. So that's the basic question. So come up and tell me how you would design a study for this, how you would operationalize, measure what you're going to measure, who you're going to recruit for your study, how you're going to what your major is going to be, and any other variables that you want to collect besides your main, what your main outcome measure, and what then other variables you want to collect. And then some specific things like, okay, if you're going to find people who have wounds, how are you going to find people with wounds, who you're going to be, etc. How long you're going to collect data for. Got it? Kind of a tough class to sort of in groups, but maybe if you could pair off, is that probably the way to do it? Or turn around? Okay, so I'll give you 10 minutes. So do the first question is that, what kind of study are you going to do? Second question, who are you going to recruit? Third question, what are you going to measure? And fourth question, for how long? Just go with those. I'll write them on the board. Go ahead and join the group. Can you read that? What type of study design? Who are you going to recruit? What will you measure? Outcome variables and other variables? And how long will you collect data and for how long? Okay, let's pause. I see people not talking. So for design, what kind of design are you coming up with? You were talking. What kind of design? Okay, so how would that work? You have to collect your own. There's no data on this. It's a new study. You have to collect your own. Anyone having a different design? Yeah. Okay, so you're going to find a group that has a wound. Okay, and then what are you going to do? Okay, so you're going to out there and find people who have been injured, and you're going to treat one with Manuka honey. You're going to give one Manuka honey, and you're going to give the other one. Okay, what kind of design is that called? A randomized controlled trial, right? Because you're probably going to randomize who's going to get the Manuka honey and who's going to get the standard care, right? Anyone have a different design? Okay, go with that one. And see if because there's also, so use a randomized controlled trial, but then in terms of how you're going to recruit people or find people, you're going to find people by just going around campus and just like ask around, or okay, like, you injured? Okay, so you're going to look for people who are around, okay, that's one way of doing it. See if you can come up with a different way of collecting information. So in your groups, go ahead and do it, okay? How else would you find people? Because there's nothing wrong with that way, but just, what would be a different way? Yeah. No. The population doesn't have to be on campus. Okay, let's take a pause for a second. So how are you going to find the people? We have one way of doing it. Look for bandages. What's another way? Yeah. Okay, so go to the local hospital. Are you going to go in the emergency room, or where are you going to go? Because you're probably asking yourself, where do people who are injured go? Right? Or where is a place where there's lots of people with injuries? So the hospital would be one. Did you have another idea? And just like start pushing kids down, like, you know, I mean, randomly pushing them down. So not you're not going to bias it. Okay, so that's a group that injures themselves a lot. Any other group that injures themselves a lot? Elderly. Okay, how are you going to find them? Okay, go to a rest home and find people. Who else injures themselves a lot? Football players, right? Sports, you know, or soccer players. They injure themselves a lot. So you can go to sports teams. But what you're thinking there is, okay, so where, because you can either, you know, do it like that, try to find a group, and that you then go to that location and you sort of say to the soccer coach, we want to recruit all the female soccer players. And every time they get an injury, we wanted them randomize them into, you know, into getting treated with one thing or the other, right? That's one way to do it. You could go to a hospital and go to the burn clinic. Right? Burn clinic would be a good place to go. And so you could, you know, go there and say, well, when patients come in, we want to go through and, you know, if they're not too bad, we want to go through and you know, recruit them. Right? So different ways you could do it. So now let's say you recruited people. How are you going to figure out what kind of injuries you're going to look for? Like, what's the criteria? Like, if with your way, who are you going to get? You're going to get people who have all different like stages of injuries, right? And they're probably going to be places that, unless you're going to, you know, look at people's legs and other things, they're probably going to be in places that you could see. If you go to a burn clinic, then the worry is that you're going to get someone who's got, like, you know, burns all over the body, and that's probably not who you want, right? So there's probably some, you have to decide, you know, who are the group that you want to specifically, and then what kind of injuries. Like if somebody, you know, gets their thumb cut off, are you going to recruit them? All right, so talk about who you're going to recruit, like what kind of injuries that you're sort of interested in, and then also what's meant by healing. That's a good question. I mean, because it's going to determine who you recruit, right? Yeah. Because you could have a research question that said that it's good at preventing infections, right? You could have a research question that says it's good at treating infections. Okay, so I'm going to ask you then two questions. Who's your group? What kind of injuries? And how are you going to measure whether it's healing or not? Three questions. I ask you three questions. Who's your group? You know, what kind of injuries and how are you going to measure healing? Okay, so go ahead and figure out the answer to those three questions. Okay, ready? Okay, let's see. Group over here. Who's your group? Elementary school kids. What kind of injuries? How do you define a minor scrape and cut? So you're gonna basically just rely upon expert opinion. Is the school nurse an expert in determining what's a cut or a scrape?
Yes. They have to have master's in.
But what's the I mean, like, what's the upper limit, right? If someone cuts their finger off, is that gonna be?
No,
Okay, so what's the line between what you're gonna accept versus cutting finger off is out of bounds? So where does the line hit? What you start gonna say? A superficial cut? How define superficial? How about this? How about say, if you can stop the bleeding without having to get stitched? What's that? Okay, all right. Group back there. What's your group? Okay, so you're gonna go in the emergency room, see someone is injured. How are you gonna identify whether they're injured? If they're injured? I mean, so you're gonna rely upon, I mean, because you could say, we're gonna go and make it, go to the doctor, the ER doctor, and say, when a patient comes in with a certain type of criteria, superficial wound, you're gonna bring along the school nurse, and she's the expert at determining these things, and determine what's the, have some criteria. Has that then, all right? Okay. Yeah. Okay. So maybe do the stop bleeding. If it stops bleeding on its own, then you'll accept it. If it doesn't, and will you accept anything? Like if the person, is there a difference between, scraping up the entire leg versus just your finger, or you take everyone? Okay. And how are you gonna identify if something's healed? Okay. But that would vary based upon the size of the cut, right? So you have to somehow.
The size of the wound.
Yeah, so you'll try to measure the size of the wound. So maybe what the whole outline of the diameter, is that the important thing in terms of healing time? Let's do this group back here. Do you have a group that you can look at? Yeah, you guys, in the back. Okay. So you're gonna go to a coach and say, whenever you've got a player get some type of injury, that's great. Okay. How are you going to determine, so you'll measure the wound like this? Is that how you'll determine and then what's healing? How do you determine healing? let's see, you're going to the, you're gonna go to the school nurse. Is that right? Were you going to? Oh, okay. Where are you gonna go? Oh, okay.
In one day,
Uh-huh.
all the singers in place. So not really have one place is around 5 acres.
Huh?
And I'm like, only like 2 areas and couldn't be for that.
Huh.
And then we'll be turning to the healing kind of stuff.
Which state park you gonna go to? Well, because it matters, right? I mean, you could go to that, you could go over here, right, to that local park. And what kind of injuries would you gonna get there? Well, I guess kids playing on, or you could go to Yellowstone and get like grizzly bears mauling people, things like that, right? So I don't know, I like the grizzly bear mauling people kind of idea, you know? Not seriously, just like little gumming them a little bit, just to kind of give them some scrapes. But at least you'll have lots of them, because you need lots of people who have similar type of injuries, right? Any other group have a different? Yeah. Uh-huh. Uh-huh. Okay, so you want to, find people who are in there for another condition, and then see whether it helps them. That's kind of like doing it for elderly as well. I mean, because there's one way you could do it is pick a healthy population and then look on the healthy population, or you could pick a marginalized population like the elderly or people on ventilators, or whatever, and do it on them to sort of see. Mhm. Would it be ethical to basically just get recruits and then give them kind of a scrape, like with sandpaper? Would that be ethical? Might be. If people recruit, and if you can, then, and that's the way they do a lot of stuff. Like, as we'll talk about with clinical trials, stage 0 clinical trials usually are clinical trials where people might die. And so they used to do those type of things a lot with prisoners. And then that was determined to be unethical to do it with a captive population who probably isn't in a position to say no. So now, like, if you notice I think it's in your ethics training, but it's if you go and you do an IRB online, they'll ask you, are you doing it with special populations? So prisoners, pregnant women, children, people with disabilities, etc. So it's kind of like groups that traditionally, you want to think, well, if you're going to do some type of research with these groups, IRB is going to be extra cautious about what you're doing. But in theory, you could do it. You could just, scrape someone up and then do it that way. I mean, IRB would have to prove it, and you'd have to really show that there's a reason for doing it, that you couldn't just do one of these other ways, but in theory you could. Okay, so now you're going to go through and you're going to, find your group of people. You're going to somehow measure the wound. You're then going to go through and give one group honey, and you're going to give another group just the standard care. And then you're going to follow them up. And at some point you're going to determine, that if they're now healed. So, I mean, healed could be is that it completely goes away, or it could be is that, it just sort of scabs over or wherever it's going to be, but you have some type of definition for how it's going to be healed. Correct? Okay, that's a randomized control trial that you mostly have said. Because, what you're doing is you're somehow finding the group, and then you're randomizing the Manuka honey versus other things. So if you think about what determines whether or not someone's going to heal, because that's what your outcome variable then is time to heal, right? How fast it's going to heal. So what determines how fast something heals? Besides Manuka honey, what else determines how fast something heals? Well, your people are going to heal slower than their people, right? How come? Because you were doing elderly, right? They're gonna heal slower than children. Why is that? Because they're Because they're your children and they're old people, and old people heal slower, just, so yeah, so just like people on ventilators are probably going to heal slower than children. Athletes are probably going to heal faster than old people. Well, athletes heal faster than children? Maybe, maybe not. So age, it's going to have one gender. Will gender make a difference? Don't know. Might make a difference. So one way to get around that is to do all female soccer teams. Another way to do it is just to only say we're going to just do it on maintenance, which is what they did in randomized controlled trials. In randomized controlled trials, part of the reason that they're criticized is because they tend to do on homogeneous populations. So they just choose, like my wife one time, when she was in graduate school, she worked on a breast cancer. There was a breast cancer drug that was just out. And so she was doing, she's a psychologist. And so she was looking at, psychological outcomes and healing and things like that, and recovery from this breast cancer drug. And this was in Wisconsin, in Madison. And when she looked at the population of these women with breast cancer, they were 95% white, and 90% of them had above a master's degree or above. So why is that? Because it's Madison, Wisconsin. And so, was that a problem with the trial? Well, the trial liked it because they had a homogeneous population. That is, that they want to have everyone as alike as possible, except for the one factor of, are you going to get the treatment or not? But the downside is that then, they don't do it in other populations. So like in this case, they didn't know if it was going to work on women of different ethnicities or different areas or whatever it's going to be. So that's a criticism of randomized controlled trials. Why did they do that? Why did they try and choose homogeneous populations? Flipped around the other way. Age is a difference, right? So therefore you think, okay, so we're going to control for age. What else is going to determine healing times? How often you wash, right? How often you wash is going to determine it. Just natural variations between people, it's going to determine it. Whether you have young kids around who are kind of diseased and infectious on all sorts of different fronts and going to be infecting you. So there's lots of different factors. So in a study, you can either try to get as homogeneous as possible to get everyone the same circumstances, or you randomize. So if you randomize, the whole idea is that yes, all these other factors are important, but as long as we randomize, is that there's no reason why this group who gets the honey is going to be systematically different than this group who doesn't get the honey. That's the whole reason why they do randomized controlled trials, is because it allows them to doesn't say that all these other factors aren't important. What it says is that you can't control for everything, but as long as you randomize, then those things are going to wash out. That is, that there's no reason to have systematic differences between the groups. It's also why when we do the studies in table 1, you always put your demographics. That's why you're looking to see, is there something weird about the population in the study compared to what the target population is. Okay, that's the beauty of randomized controlled trials. Also means that you can only look at one thing, basically, right? Or you only have to look at one thing, which is that did the Manuka honey lead to better healing outcomes? Okay, let's see. An alternative design would be an observational study. So what you do is that you go out there and you could find people who are using Manuka honey, and you could find people who are not using Manuka honey. So maybe advertise, right? Or go to a shop. Go to a shop where they sell Manuka honey. And when someone comes in, you recruit them. And then you go to a shop and you recruit those who are buying Manuka honey, and you recruit those who are just buying a standard, Bactine or whatever it's going to be. So if you do that, you're not randomizing, correct? So what's the problem with doing it that way? What's the problem with doing it in a way such that when you just do an observational study and you're just going to look at people who buy Manuka honey and you're going to just compare them to people who don't buy Manuka honey? But this way, is this group different than that group in other ways besides just using Manuka honey? Uh-huh.
So, like, if you look at that, differences.
So they're going to be different, different income brackets, probably different living conditions, lots of different things. So observational studies are good because you're not having to randomize in this case, right? You don't have to worry about, well, you don't have to worry about giving people something they don't want. So this group over here gets injured. Maybe they want Manuka honey, but you're going to, by being in the study, you're going to say to them, no, we're not going to give you Manuka honey. Instead, we're just going to give you this standard care. And you got people over here who are being told to put the Manuka honey on, and they think, I don't want Manuka honey. So an observational study, from an ethics standpoint, allows you to avoid that because you're just letting people choose. The problem is that these people might be different than these people. And so you have to then think, well, all right, so how do I think they're going to be different? And so income is one way. What other ways how would I know? Or what could I do to look up to predict how these people are going to be different than these people? Well, you go and you read the literature and you think, well, let's take other alternative medicines. And how do people use alternative medicines different from people who don't use alternative medicines? And then that's what you measure. So income might be one thing. Could also be, I don't know, how much you like Gwyneth Paltrow. And so maybe that's another thing. So we'll measure that as a difference between the groups as well. Just lots of different things. But that's why you go and you look at the literature to sort of see. Okay. So then when you get to the measuring part, how do you figure out? Well, so we decided upon time to heal. How would I know that that's a good measure? I mean, you could have used something else like, I don't know, amount of liquid coming out of the cut or something like this. How would I know this? How would I know what to use? Well, one way is to go look at the literature and see what other studies have done. So one of the main reasons why you go through and you look at the literature is because it's going to answer a lot of these questions for you, like how specifically you do these things. And besides just sort of helping you, it also is going to protect you at the end. Because if you decide that you're going to measure it by coming up with your own kind of measure of wound healing, and you send it off for peer review might say, forget it. This is a stupid way of doing it. It's not validated. And so therefore they reject your study because you didn't use a validated measure of wound healing. You could also do it like they were talking about, get experts in, right? If you don't have any type of criteria, then another way to do it is that you get a whole bunch of experts and that you let the experts determine that. In this case, I just went and looked and found this, the development of an interesting for measuring healing, which, so if I was doing this study, I would go and I would start by looking at this to see how they did it. Okay, so then you go and you gather data. And that, let's say that, so you have your two groups and that somehow you identify time to healing as going to be your outcome variable that you're going to follow. And that you get the data, average number of time here and average number of time there. So let's say that for this group who gets the Manuka honey, you're at 22.3 days. And for this group who gets the standard care, you're at 35.6 days. My null hypothesis is that there's no difference between the groups. I get these two different numbers. Does this tell me that there is a significant difference between the two groups? And what does that mean? Well, it's saying is that, let's say 36.5, 35.6. It says that, well, so you've gone up and gathered data, and that you found that this number, you found that the average number of days for the standard care is 35.6 days. If I were to do this again, with another group, right? So again, another group, do the same thing again. Would I find it to be 35.6 days? If I were to do this again with another group, I go out there and I get another group, I give them Manuka honey. Would it be 35.6 days? What do you think? Would I, if I did it again, would I get the same number of days? No, I wouldn't. I'd get a different number. Might be higher than 35.6, might be lower than 35.6. I get a different number. Why is that? Because it's just a random sample of, 15 people, 20 people. And so therefore, if I get their number and I get 20 other people, I'm going to get a different number. And if I did this over and over again, got another group of 20 in, got a sample for them, recorded it, got another one, got a sample for it. What would the distribution of all of these things look like? If I mapped all these means, what would it look like? Wow. Anyone taking statistics? Well, the idea is called the central limit theorem. And the central limit theorem says, let's say if you have a distribution that looks like this. Well, I don't know, this is, let's say this is in time 50 years. And there's one group that's around 10 days, and one group around 30 days, and one group around 50 days. Let's say it looks like that. So it's this weird looking distribution. If you took a sample of these people, and you get a mean of 36.5, and then you took another sample, and you got another mean, and say it's 40.2. And you took another sample, and you got another mean. In each case, your sample size is 20. So you pick 20 people from each of these things, and you get your mean. And this time it's 30.1, and then it's 32.3. And so all the way down, you do this 1,000 times. And then you figure out what this distribution looks like. What that distribution looks like is this. It's a normal distribution, and it's centered around the true mean. The true mean. It's centered around it. And it doesn't matter what this distribution looks like here, is that it always has a normal distribution. That's a simple limit. That's why, we can always, when we go to and we do statistics, or when we do statistics, you don't have to worry about what the data looks like, the real underlying distribution, because you know that if you take a sample, and then you look at the means, because this is the distribution not of the data, this is the distribution of the means of the data, is that it's going to look like that. What happens if you increase your sample size up to, let's say, 300? What happens to this distribution? What happens to the shape of this distribution if you increase your sample size? Well, if you increase your sample size, what happens is that this distribution goes like that. And so this is n of 300. And if you have an n of 3 million, then your distribution looks like this. Always centered on the center of the distribution. That's why sample size matters, right? It's like, Rudy is looking at hospital data. Hospital data, Rudy, how many observations are there in the hospital data set that you're looking at? 39 million? 39 million observations. So that means that if you look at is anything in that variable, in that data set going to be quote unquote significant? The answer is going to be yes, because you have 39 million observations. So it means that your distribution is basically just a spike like that. Right? So, but it also means that sample size, is going to determine kind of how close this thing is. But sample size, it doesn't impact the true mean. It's always centered around what its true means. Okay, following that so far? So now let's say you go out there and you get this data, because you're not going to do 1,000 samples. You're only doing one sample. So you do one sample and you get a mean of 36.5. So the question is, what is that? You don't know what that true number is. So what is it? Well, what's your best guess of what that true number is? 36.5. That's the only data that you have, right? So you're gonna assume that it's 36.5 is the mean of that distribution. Because that's what you have for your control, you have 36.5. So now you go out there and you get a number, 23, 22.3. So now you get this one for the Manuka honeybee. You get 22.3 days. So if you were to go through and sort of plot where this thing lies, well, 22.3 lies right there. So the question is, could you get an example of 22.3 if the true mean was 36.5. That's the question. Could you get, if this was the true mean, right? Could you get a number like 22.3 if that was what the distribution really looks like? Could you? Yeah. You could get one, right? Because it's, the distribution, this thing goes way, way. So you could get a number of 0, potentially, or you could get a number of 1,000, potentially, because this thing just sort of gets smaller and smaller. The probability of doing that is really, really small, but you could get a number like that because it's random. You don't. It's a random. You're only taking a sample of 20, so you could get a number like that. So for when we go through for hypothesis testing for statistics, then this is not the question that you're asking. The question you ask is, how likely is it that I would get a sample equals 22.3 if the true mean was 36.5? That's the question that we look at hypothesis testing. And so how do you figure this out? Well, in statistics, but what it basically does is it looks at this here and it says, okay, so if you go that way or go that way, so you're into some area here, what's this probability in here? And then what's the probability of being somewhere outside of that bound? And if this thing is, this is called a P is less than a certain number, then you say, oh, it's unlikely that you would get that value if this was a true mean. What's this P that we're going to look at? P less than 0.05. 0.05. That means that less than 5% of the time, you would get a number like 22.3 if your true mean was this. So what it's saying then is that you're testing whether it looks like this, whether this number here comes from that, or whether it comes from something where the pen doesn't work, or whether it's come from a distribution that looks like this, that's centered on 22.3. And so the reason that we choose 0.05 is because 0.05 is basically 1 in 20. So it's saying that you have a less than that. So let's say it says if you were this type of if your true mean was 36.5 and you got a number of 22.3, that would occur less than 1 out of every 20 times. And so therefore, we reject the null hypothesis. We say this number here is unlikely to have come from that distribution. Instead, it comes from a different distribution. Make sense? Okay, what if you got a sample of 300? Well, now if you got a sample of 300, 22.3 is going to be way down. So it means that you're definitely going to conclude that it didn't come from this distribution. Right? It's not consistent with coming from that distribution. And if you have 39 million people then, 22.3 is down here someplace where it's infinitesimal probability. So that's why if you think about what the null hypothesis is doing, the null hypothesis says, all right, I'm going to say that, that there's going to be no difference between this and this in the sense of that they both come from the same distribution. That's my null hypothesis. And so I'm only going to reject my null hypothesis and conclude that this thing is different if this number here, 20.3, occurs only less than 5% of the time. Doesn't mean it can't occur, but just less than 5% of the time it occurs. And so therefore, if this P is less than 0.05, then you reject the null hypothesis. Does that mean that we've proven that this number here comes from a different distribution than this, or put it in more common terms? Have we proven that Manuka honey is better at healing than standing prayer? We've proven that Manuka honey is better than standing prayer. Well, the way to ask that is to say, well, could you get a number of 22.3 days if there was really no difference between standing prayer and Manuka honey? Could you get that number? Yes. It's highly, highly unlikely you'll get that number, but you could get that number. So therefore, we haven't proven it. You might do the next study, and the next study for Manuka honey gets a mean of 37.5 days up here. And you might do it again, and you get a mean of 29.2 days. So it could be is that this is just an outlier, and then you've only gone through and you've got this result just because it's just by chance. It's happening like that. Make sense? So that's why when in statistics, you can never say that you proved anything. In fact, it bugs me. Bugs me in scientists when I hear scientists say this. They say we've proven this, and I always think, ooh, I know they're trying to sound definitive, like these people shouldn't argue with them, but technically, you never prove anything. What you can say is you can say, well, all the evidence points in this direction, but you never can really say you proved anything in statistics. And I'll put that on the test. Can you prove anything in statistics? And you have to tell me no, and you have to tell me why you can't prove anything in statistics. Because it's another thing, like with P, after you get tattooed, P less than 0.05 on your forehead, I want you to also tattoo. You can never prove anything in statistics, because technically you can't. All right. But that's why when we talk about science setting up a tough test, it's saying is that science is setting up a test whereby if for you to reject the null hypothesis, is that it can only happen by chance less than 20% of the time, 1/20th of the time. Doesn't say it can't happen less than that. So why? But just saying is that it's just unlikely to have happened. It's less than 1 of every 20% of the chance that you get that number if they were really from the same distribution. How did we get this number of P less than 0.05? Why not P less than 0.10 or P less than 0.001? Why P less than 0.05? I have no idea. It's always been used. In some disciplines, like, my wife works in psychology, they're dogmatic about P less than 0.05. In other areas, like in public health, you can publish with P less than 0.10. You can do that and sort of talk about trends, but it's just the convention in science of P less than 0.05. There's probably some deep reason that someone at some point came up with this, but I've never been able to find it. They don't use this P less than 0.05 in everything, right? So oftentimes when they test for drugs that can have negative side effects, and they're looking at the number of side effects for a drug, they don't want to sort of, this is a very conservative way, right? 1 in every 20 is a very conservative, or by that it means it's hard to reject or not. But for things that you want to make it easy to reject, so for example, if you say, are there side effects from this drug? And that, and you do it and 19% of people get side effects, but then you go through and you think, oh, well, out of P less than 0.05, not that big, it's not significant. Well, for things that are bad for people, they typically say, we're not going to use P less than 0.5, we're going to use P less than 0.50. So they make it an easy test to reject the null hypothesis. So there are cases where they change around this significance level, but for 98% of the things that you're going to see, it's going to be P less than 0.5 is what they use. All right. But that's why they come up with the conclusion is that science is very conservative, because what you're doing is that you're making you're saying my research question is, Manuka honey is good. I then go through and I put this null hypothesis is that Manuka honey is no better than standard care, and it makes a tough test for Manuka honey to kind of be proven as good, not proven, to be consistent with to reject the null hypothesis. They make it a tough test to reject the null hypothesis. Okay, so let's see if you can answer these questions. Why 2 groups rather than just one? Why wouldn't we do a randomized controlled trial to use 2 groups, not just 1 group? Need a comparison group, right? Why change only 1 factor? Why not change several factors? Yeah, because then because you won't know. Like, let's say if you gave these people Manuka honey and you had them watch videos, cat videos, and you gave these people standard care and you had them watch, Australian rules football, is that then you wouldn't know whether or not the better healing was from the cat videos or the Manuka honey. What about factors that you can't randomize, like how much coffee people drink and things like that? Why don't you have to worry about those things? So why don't I have to worry about all the other factors I think are going to influence healing, like coffee drinking and how many kids you have and things like that? Do we?
I guess it's around people like coffee or don't drink coffee, so the results can vary depending on their data habits.
That's right. As long as I don't choose my Manuka honey group out of people who drink more coffee than the people who don't get the standard care, I don't have to worry about it. Because that as long as they're on average equal amounts of coffee drinkers in each case, that it's okay. That's why when you randomize, you want to really randomize. And you don't want to have it so that all your coffee drinkers are on one group and all your non-coffee drinkers are on another group. Because then you're basically varying 2 factors again, right? You're varying Manuka honey and coffee drinking. If you truly randomize, should take care of that. Okay. Why have the experimenter blind to the conditions? Because that often happens is that if I'm the person who's running the study, I won't actually be the one who gives people Manuka honey or gives people the standard care. Why is that? Yeah, how can it? But if I randomize, how can it bias? Well, because I could do things like say the Manuka honey people, you all look great today. This is going wonderfully. You're really healing well. And to all the standard care, I'd say, ooh, that wound looks bad. Right? So I can influence the results. So what a double-blind experiment means is that a blind experiment means that I don't necessarily, I'm not going to know who's going to get what. What's a double-blind experiment? Yeah. Right. So basically, I would give you standard care that looks and tastes like honey, and I would give you Manuka honey. And so no one would, because you're going to know if you have Manuka honey, right? But so I want to make it so that that you think you have Manuka honey too. This happens a lot in cancer trials, whereby the group who gets the standard care, knows pretty fast that they're in standard care, and so what they could do is they drop out the study because then they know they're just getting the regular treatment. And in cancer is a particularly kind of tough arena to be doing research in, because the people are usually so desperate about wanting to get treatments, is that, they're not willing to rely upon the standard treatment. They want the new treatment. So what happens, one of the problems in cancer treatments is trying to get the people who are in the standard care to stay in the standard care and not drop out the study. If you reject a null, have you proven the groups are different? If you reject a null, have you proven that the groups are different? Show me, yes, you've proven it. No, you haven't proven it. Shh, no, you haven't proven it. You have given evidence to consider that says it's very unlikely the groups are the same, but you haven't proven it. And why p less than 0.05, less than p less than 0.10, and less than p 1.5? The way it is. So, okay. So you've done your study, and now you've come through and you've done this test. You can also see is that when you write up your study and you write up your results, what you're really writing when you get to the method section is you're writing a cookbook. That is that you're writing instructions for how someone else can do exactly what be able to do exactly what you do and replicate your results. And that's really important because, if it's all based upon this idea it's based on this idea that, that here's your true mean, 36.5, you get 22.3. And that you then sort of say, oh, this is going to occur, this number would occur less than 0.05 of the time. Right? That's what's based upon. So now the idea is that somebody else should be able to pick up and do exactly what you do and replicate your results. Will they also find? So let's say that, what you've said is you said, okay, I do this and I reject the null. I reject a null, and I say that really the distribution looks like this. It's centered around 22.5, 22.3. That's really what you're saying. So someone else should be able to pick up what you've done, and they should be able to replicate it. And they should be able to see, do they also reject the null hypothesis? Now, will they, if they do it again, will their control group be 36.5? No, it won't be. It'll be some number. It'll be some number within this distribution. But it won't be. But could the control group be 22.3? Could the control group have a number of 22.3? Yes, it could, right? It would occur less than 1 out of 20 times, but they could do it. So they're going to get some number, and let's say they get a number of like here, 30.1. That means that they're going to say, well, their distribution actually looks like that. And let's say that they find that they don't get 22.2, they get 24.5. So they're going to get different numbers. So they could come through in that they could say, oh, well, wait, we don't reject the null. Does that mean that your conclusion was wrong? Does it mean your conclusion was wrong in your study? No. Given your evidence, that's what you do. But it's possible that somebody else could, even if these were the true distributions, right? If they were really different, they could come through and do a study that would then not reject the null hypothesis. But the idea is that if you did lots of different studies, is that pretty soon they'd go back to being centered around the true means. And so you would have, on average, you start having people rejecting the null a lot more. So that's the idea of in science, is that you should be able to write the results so that someone can replicate exactly what it is that you've done, and that they should be able to do the study. And that when they do the study, they should be able to go through and to find, and come up with results that are consistent with what you're doing. That doesn't mean they're always going to replicate your findings, but it does mean that that they should be able to replicate your study. And if you do a lot of these different things, then, then it should be on average is that if these things are, are the real kind of means, that's what you should get out of the different studies. So the problem is that there's what's called a replication failure problem. I'm not sure if you ever got wind of this, but it's hit mostly in psychology, mostly in social psychology. It's because there's a series of different studies that have been done that people can't replicate. So that's a good one. That's a good example of one that's been done that they can't replicate. I know, sending around poll workers to like a single poll worker going to houses, and it's been found that study came out that said that was enough to shift votes by like 10% towards the candidate who that they were polling for. So it was a randomized control trial. They went out there and they did half of the Confederates, the team of interviewers went and promoted the Republican candidate. The other half did the Democratic candidate, and then they looked to see about the poll results and everything. This came out. This is one that had horrible problems being replicated. And so the question is why? Why couldn't anyone ever replicate it? Well, one reason could be is that they falsified data. And there's been a number of different studies that come out in psychology, in social psychology primarily, where they found that they changed the data. As that, what they did is that they would just get the data and then go through and just change values until they got p less than 0.05. So that's bad. You can do a lot of things in academics and not get fired. You do that, you're fired, and yet you'll never get another job. So that's really, really bad. And just for this reason, because the whole scientific process, kind of depends upon you being an honest person in your study. And so if you show that you're going to do that, then you're out. No questions asked. Okay. So that's one reason people falsify it. Another reason could be is that, well, it was just a random chance, right? In fact, this happens a lot because if you're doing a laboratory type study and that you can bring in subjects and then bring them in again and bring them in again and keep doing this, is that eventually you're going to end up with a significant result, even if what you're doing is not significant. What percentage of time will you end up with a significant result, even if your study has really no impact? Is that if I were to let's say that there's no difference between Manuka honey and standard care, but I kept doing the study, what percentage of time, how likely would it be that I would finally get a sample that looked like they were different, even if there was no difference? 1 out of 20, right? 1 out of 20 times I would get a sample that showed there was difference. And 1 out of 20 times I might also get a sample that shows if standard care was significantly better. But if I ignore those other 19 and I just focus on just publish the one that said that there's a difference, then that's another way that you can kind of have non-replicable findings. And then the other way is that well, what if in doing this study you just do a crap study, right? You don't administer the Manuka honey correctly, or that you don't randomize correctly, or whatever it's going to be. So when I replicate it, is that I don't replicate it well, I do it really, really poorly. So if I do it poorly as a researcher, then I'm not going to find differences because I'll basically just contaminate the study, right? I let these people use Manuka honey, not these people. So, but again, it's going to show that there's no significant differences as a result, but not because the original study was flawed. It's because the people who replicated was screwed up or was not very careful. So this has been so in science, the ability to go through and to falsify something is critical to what we do. At the same time, it's really problematic, and it's very controversial right now because there's a lot of studies that are going on and trying to it's the failure to replicate problem that's going on right now, where they're coming out and saying, oh, look, if this means that the original people lied or manipulate data or whatever, but it can be a lot of reasons that have nothing to do with that. It doesn't happen so much in our area because, like, Rudy getting the hospital data, going to go through the hospital data and see whether or not things are different. Rudy would have to change a lot of different variables in order to to get it, to change, significantly change the results. And also anyone else can get the hospital data and do it. And so when we use a lot of secondary type of data, is that we tend to not have that type of problem. It only becomes a problem when you're collecting the data and you can manipulate the actual data itself. Okay. All right, well, why don't we stop there and we'll start there on Thursday.